what we learned today is that it is hard to realize combinatorial structures as polytopes. Okay, and I guess the official title for this second lecture will be Realization Spaces of Polytopes and Oriented Matrix. And before starting, let me advertise a small book by Jürgen Richter-Gebert called Realization Spaces of Polytopes, which is where I learned most of the things I'm gonna tell you today. Okay, it's a very nice book. So let's start again with a polytope. It will be a d-dimensional polytope with n vertices. And today, to make our lives simpler, I'll ask the vertices to be labeled. Okay. So you have a label to each of the vertices, let's say the numbers from 1 to n. Okay? And now the realization space of P will be the set of all realizations of P, which is the set of all polytopes that have the same combinatorial structure as P. Okay, so formally, the realization space of P. So now we are in dimension D, and we have n vertices. So each vertex has d coordinates. So if we record all the coordinates of the vertices, we can put them in a d times n matrix, right? So this will be my realization. It will be a d times n matrix. And you see why labeled is important, because the order of the columns in this matrix will matter. Okay? Essentially, this is there to kill the symmetries of the problem. So I'll take all the matrices such that the convex hull of these endpoints has the same combinatorial structure as P. By the same combinatorial structure, I mean the same phase of lattices, lattice of faces, but labeled. Okay, so I want to say that this polytope is combinatorially equivalent to like something like this, 1, 2, 3, 4, but it should not be the same as 1, 2, 3, 4. Okay. I want the same subsets of vertices with the same labels to form faces in both polytopes. Sorry, yes, definitely not the same. Okay. And what we want to understand is this set and how complicated it can be. Okay. And if you start in dimension 2, this is okay. Okay. Let's say you have two realizations of a quadrilateral. And for example, you want to go from one to the other. What you can do is maybe like push a vertex, let's say the vertex 3 on top of the edge 2, 4. Now you have a triangle. You can continuously move this triangle to this triangle here and then pop back the vertex 3 here. Okay? So it just proves you that this realization space is connected. In dimension 3, things are nice still, and this is mainly due to Steinnitz's theorem. So I'll need another result first, which is Witten's theorem, which we can summarize as a three-dimensional polytope is determined by its graph. So if you know the graph, you know all the faces. Okay? This is no longer true in higher dimensions, but in dimension 3, if you know all the vertices and all the edges, you can guess who the two-dimensional faces are going to be. Okay? So to realize a polytope, you only need to check the graph. And Steinitz tells us that it is easy to decide which graphs are graphs of three-dimensional polytopes, okay? Which will tell us that it is easy to decide which combinatorial structures can be realized as three-dimensional polytopes, okay? He says G is a graph of three-dimensional polytope if and only if G is three-connected and planar. So that the graph of a three-dimensional polytope is planar. This is quite obvious because, you know, take your three-dimensional polytope, put a point inside and push it onto the sphere, so you have a drawing on the sphere. And now if you want a drawing on the plane, just do stereographic projection. Okay, so a graph of a three-dimensional polytope is obviously planar. And three-connected means that if you remove no matter which pair of vertices, the graph remains connected. And this is also not hard to prove. This is Balinsky's theorem. So one direction is clear. What's not so obvious is the other direction, that no matter which three-connected planar graph you have, it is the graph of a three-dimensional polytope. We could say that this theorem is like the first theorem on polytopal realizations, right? Like you have a combinatorial structure, you have your favorite three-connected planar graph, and Steinitz gives you a way of finding a convex three-dimensional polytope with this graph. And there are several proofs for this theorem that give you, like, again, new perspectives and nice, and you learn nice things, and in particular from the proofs, you understand quite well the structure of the realization space of a three-dimensional polytope, okay? And from the proofs, you see that this realization space of a three-dimensional polytope is a ball, okay? It's an open ball of dimension number of edges -6. So this is a very precise statement. In particular, it's contractible, so you can go from any realization to any other continuously without changing the combinatorial type along the path. It contains rational points. D polytope is a d-dimensional polytope, so here d is equal to 3.
In the space of configuration, should that be in d+1? This is a 2 polytope, right?
This is a 2 polytope, so here I will have 2 times 4 coordinates. So here I'm recording the coordinates of every vertex. No, it's okay.
And another question is about if you change the orientation?
Yeah, so I'm cheating a little bit. So these clarization spaces are not connected if you don't mod out by change of orientation. So if you have 2 mirror images of the same polygon, you cannot go from one to the other. And actually what we do is we mod out these affine transformations. So maybe, let me put it here. Yeah. Thank you. Yeah, this is better. Otherwise, it's not true. You always have, like, any affine transformation sends a polytope to something which is equivalent, and you always have that in your realization spaces, so you can just mod it out, and then you have more meaningful.
Is that why you have -6?
I guess so, yes. It contains rational points, which means that if you have your favorite three-dimensional polytope, there is a realization of a combinatorially equivalent polytope with rational coordinates, okay, and therefore with integer coordinates. every combinatorial two-sphere is polytopal. Here I'm a little bit vague on what a combinatorial two-sphere is, but let me keep it that way. The thing, you choose your favorite graph, okay, you draw it on it's reconnected and planar, so you get something which is just combinatorial or topological. You know that there will be a rational realization, a convex realization, okay? Which is not what will happen in higher dimensions as we saw yesterday. And you can prescribe the shape of a facet. And what do I mean by that is you have your favorite three-dimensional polytope, which has facets that are polygons, and you want to draw it, okay? Well, you can start by drawing any of the polygons. You choose your drawing of the polygon, and then you'll be able to build the polytope on top of that, okay? So you can decide how are the two-dimensional faces going to look like. Okay. All these statements are false in dimension 4 and larger. Okay, and this is what I want to tell you today.
Can I just ask, is the contractibility the result that people often use to deduce connectedness of the flip graph or triangulation?
No, because this is a fixed combinatorial type. When you do flips on triangulations, you're changing the combinatorial type.
Okay, here you go.
Yeah. Sure.
Define what's combinatorial two-sphere, or what you mean by that.
Take a strongly regular CW complex, which is homeomorphic to a sphere. So the first result I want to show you is that there are polytopes that you cannot realize with a rational coordinate. Okay? This is a result of Perles. And he proved first that there is an 8 polytope with 12 vertices and 28 facets with no rational realization. And to show you that, I have to do a small parenthesis on oriented matrix. So imagine you have a point configuration A, okay? And I want to store some combinatorial data, which is the following. I'll take all hyperplanes, oriented hyperplanes, so they have a positive side and a negative side. And for every point, I will look at which side they are, and if they are in the positive side, I'll store a plus. If they are in the negative side, I'll store a minus, and if they are on the hyperplane, I store a 0. Okay? And I do that for all possible hyperplanes, and I get a collection of sign vectors. Okay, so I get vectors that have pluses, minuses, and zeros. Okay, so this is 0 plus minus 2dn. Okay, I'll say that this collection of sign vectors is the oriented matrix associated to the point configuration. Okay, I won't say much more on oriented matrix, so the real definition of what an oriented matrix is there is a series of axioms which are verified by these sign vectors associated to point configuration, and you say that an oriented matrix is anything that fulfills those axioms. Okay, but I think that it's enough if you understand what I mean with the one that is associated to a point configuration. So I'll give you, let me write the definition. So these are the covectors of A. I take the sign of f of a1, f of an for all f affine map. Okay, so I take one affine functional and I look at the points that are negative, 0 and positive for this affine functional. I'll take all possible affine functionals, so all possible hyperplanes, and I look at all the partitions induced by those hyperplanes, and I store that. And this is the oriented matrix associated to a point configuration. I guess it's here. Okay, so what Perles did essentially is to consider this point configuration. Okay, so and like you just draw these with the right collinearities and consider all the realizations of this point configuration. And if you try it, the first thing you realize is that this is projectively unique. What do I mean by projectively unique? Is that there is only one realization up to projective transformation. Okay? If I take these 4 points, for example, they form a projective basis. Okay, so if I mod out by projective transformations, I can fix the coordinates of these 4 points. And what I mean by this being projectively unique is that once I fix the coordinates of these 4 points, I know the coordinates of all the points. Okay, so there's a single realization up to projective transformation. This is an easy exercise. So you know, like first there are some coordinates that are given. You know, like this point is the intersection of these 2 lines and so on. Then let's say like this one depends on one parameter because it's on this line. And then if you keep going fixing this one parameter, at the end there is, you know, this line and this line and this line have to cross at a single point, and this gives you an equation, and then you have a single solution for that parameter. Okay, so it's not hard to see that there is only one realization up to projective transformation of the oriented matrix of this configuration. And now the thing is that realization will need to use non-rational points, because actually the cross ratio of these 4 points is not rational. So any realization, if you do, it doesn't matter the projective transformation because the cross ratio is a projective invariant. Any realization will need to have at least one point with non-rational coordinates. Otherwise, this cross ratio would be rational. So this shows, even if I have not defined it, that the realization space of that oriented matroid does not contain any rational point. And now, what we want to do now is to say a similar statement about a polytope. So far, I have only an oriented matroid. And there is a trick due to Lorentz that lets you transfer properties of, like, lets you encode an oriented matrix inside the phase lattice of a polytope. So the idea is the following: take that drawing and put it on the plane in R3. Okay. Let me simplify that drawing into a pentagon. Okay. And now take one point, and what I'll do is I'll replace this point P by 2 new points, P plus and P minus, in one dimension higher. And these 2 points, they must make a line that intersects this plane on exactly this point. Okay? And I will say that this is the Lorentz extension of this point configuration at P. Let me just tell you with this picture the crucial property that this one has. And it's the following. If you, yes?
P is one of your points?
Like now I'm defining it in general, so P would be a point of any oriented matrix. Here I will do it on each one of the points of my configuration. But yes, It's one point of your oriented matrix.
There's not a projection. It's just each point you choose a different line.
Exactly. Yeah. So you will keep increasing the dimension. That's why you get a high dimension with that parallel construction. So if I do the convex hull of what's left on the plane and P plus and P minus, if P was on the line spanned by this edge, then I will have a square face. Okay? If P is, let's say, beyond the line spanned by this edge, then I will have a face with P minus. And if P is beneath a line spanned by a face, then I will have a face when I take the convex hull with P plus. Okay? So you can see in the convex hull of this extended polytope, so now I'm only looking at the boundary, I get some properties on whether this point is at one side or another of hyperplanes. Okay? I mean, this is, of course, you have to do the work, but this is the key of this construction.
Can you explain how you decide how you go to P minus or P plus?
No, okay, so there's two things. One is P plus and P minus, you choose whatever, you take 2 points on this line. And beyond, I mean, there are some lines that separate the polytope from P. If the line separates the polytope from P, then I will get the convex hull with P minus. And if the line does, if P and the polytope are at the same side, then I'll get the convex hull with P plus. Okay, and this I will call it the Lorentz extension at P, and the Lorentz lifting it will be the Lorentz extension on each point, okay? And then I take the convex hull and I get the Lorentz polytope. The Lorentz polytope is the convex hull of, so we'll call it LA, is the convex hull of this lifting. Okay. I mean, this is of course very technical, but the important part is that this technique allows you to transfer properties of the oriented matroid onto properties of the polytope. So everything you knew about lines and sides of hyperplanes and collinearities, now this is encoded somewhere in the phase lattice of this polytope. Okay. So every realization of this polytope encodes somehow realization of the oriented matrix you started with. And if you had no rational points in any realization here, then, so if you could not find a realization with only rational points here, you cannot find a realization with only rational coordinates here. Okay? Or say differently, if you had a realization with rational coordinates of the Lorentz polytope, then there would have been a realization with rational coordinates of this configuration. So this proves that there is a polytope that you cannot realize with rational coordinates. If you check the dimensions of when I told you like Perles, it won't match because Perles was very clever. Okay, so he did some tricks to reduce. So he doesn't do Lorentz lifting on every point, only in those that are needed. He also, like, you don't need this point for this to be projectively unique. So he removes this point, and then he doesn't work on this oriented matrix, but it's dual. Okay, but the main ideas are there. So this is the first example of a non-rational polytope. Okay, any questions?
Is this the smallest dimensional non-rational?
No. So if I'm fast enough, at least I can say it now because I won't give the proof. You have in dimension 4 already. There are counterexamples. Yeah. Okay. Okay, let me give you the second example of like, this is how the story developed. Like first they thought, well, realization spaces of 3 polytopes are nice, so realization spaces of 4 polytopes should be nice. Let's try to prove it. And then they started realizing that like funny things happen, right? Like first the non-rational polytopes. So now I'll show you a polytope that you cannot prescribe the shape of a 4 polytope that you cannot prescribe the shape of a 3-dimensional face. Okay. So here you have an octahedron. I hope you can read my picture. Okay. And I selected a polygon on its boundary. So I'm looking for a realization of the octahedron. It won't be a regular octahedron for which there is a point, like somewhere here, that the boundary that it sees is exactly this red path. And that octahedron should look something like this. Okay, I'll let you think about it. This is the best I can do with my drawing skills. So it's not a regular octahedron, the octahedron we are looking at, okay? But it has the same combinatorial type. And there will be a point, if you want, the point is at infinity, okay? That when you cast the shadow from that point, this is exactly what you see, okay? And this is essentially, like if you lift this picture, this is the realization we're looking for, okay? Hope you can convince yourself that this might be possible, okay? It is possible. So do you see the octahedron here? These 4 points here are these 4 points here, but you don't realize them flat, but twisted. Okay, this is so essentially what you can take is just take a regular octahedron and twist this edge up and the other edge down. And then you get a picture that looks like this. And now you take this point that was seeing this, that I placed at infinity, and you do a Lorentz lifting on that point. Okay, so now you get a 4-dimensional polytope, and this 4-dimensional polytope, we did this Lorentz lifting, so we left this in a hyperplane. Okay, so all this octahedron is in a hyperplane, so this is a facet of this 4-dimensional polytope, and this Lorentz lifting knows that the shadow boundary from the point P that we lifted looks like this. And if your octahedron looks like this, these 4 points cannot be coplanar. So you cannot start your picture with a regular octahedron and then build this polytope on top of it. Does this make sense? So this is one example of a non-prescribable 3-phase of a 4 polytope. This is due to Kleinschmidt in 1976. And this is the main piece for another 4 polytope, which is due to Bokovsky, Ewald, and Kleinschmidt, which works as follows. So let me draw this polytope like this. Okay, so this is the octahedral phase, and then there is something on the other side. And now I'll take a mirror image of this polytope. Okay. And they both have an octahedral phase, and combinatorially what I'll do is I'll remove the octahedral phase here, the octahedral phase here, so maybe. So I have these 2 mirror images with this octahedra. I remove this octahedron, and I glue them through the boundary. I do this topologically, okay? And I get a 3-dimensional sphere if I look at this as the boundary. And this 3-dimensional sphere turns out to be realizable as a polytope. But these points here, they put a condition on this polytope that that these 2 edges are twisted this way. But this you have the opposite condition, telling that you're twisted the other way around. So this connection cannot be flat. There cannot exist any octahedron in between both because you're putting contradictory conditions. Okay? Does this make sense? So I take one that's telling you, well, the octahedron, it's twisted to the right, and the other one tells you the octahedron is twisted to the left, so there can be no octahedron. And what happens is that in this realization of these 4 polytopes, these 6 points, they do not lie in a common 3-dimensional hyperplane. They are like bended to one side or to another. Okay, and now take 2 copies of this one, but mirror images, one of the other, and try to go continuously from one to the other, and you will not be able, because like you would have to find a flat octahedron in between, and you know that the flat octahedron is not possible. And of course, this is a little bit hand-waving, but this is the first example of a polytope with a disconnected realization space. Okay, so you have realizations where, you know, like this non-existing octahedron is like bended one way, and the realizations when this non-existing octahedron is bended the other way. And you cannot go from one to the other, because in the middle you would have the octahedron that cannot exist. So this gives us 4 polytope with disconnected realization space. Bukowski, Ewald, and Kleinschmidt.
What did you say then at the beginning about connectedness of the representations?
So for 3-dimensional polytopes, it is connected. Only for 3D. All what I said at the beginning is false in dimension 4 and higher. So my goal is to show you that these realization spaces are as complicated as you can imagine. And this is the first symptoms that they can be disconnected. And all these symptoms will be like encapsulated into one big hammer, which is Neuf's universality theorem, that says like anything bad you can imagine, you can find it in the realization space of a polytope. Okay, this is Neuf's universality theorem. It's 1985. It says the following thing: for every primary basic semi-algebraic set S, there exists an oriented matroid whose realization space is stably equivalent to S. Okay, so a semi-algebraic set, here is a set that is described by polynomial equations and inequalities, okay, with integer coefficients. It is, well, usually when we say semi-algebraic set, we allow unions of those, and here I won't, so that's what's basic, okay? And primary is that the inequalities that I'm looking for, they will be strict inequalities. Okay, so you have either identities or strict inequalities. So this is a primary basic semi-algebraic set. Okay, so this is a quite large family. And then you give me your favorite primary basic semi-algebraic set, and Neuf will find an oriented matrix actually of rank 3, which means something that looks like a point configuration. So the rank is like the dimension plus 1, essentially. whose realization space is stably equivalent to S. Okay, so which is as bad as S. So this stable equivalent is like some kind of homotopy equivalence, but that preserves also like some algebraic properties. So for example, like if one doesn't have rational points, then the other won't have rational points either. Okay, I'm not sure. Well, let me just say it orally what it means. So this is the equivalence class by rational transformations. You mod out rational transformations. And then you mod out what's called an stable projection. And a stable projection is a projection where the fibers are polyhedra whose boundary is defined polynomially on the variables of the image. Doesn't matter. It's a strong homotopy. Like it's a very nice, strong homotopy equivalence. Okay, so it says. Like semi-algebraic sets, you have a lot of freedom, so you can do many nasty things. In particular, of course, no rational points, or disconnected, or actually like any wild topology you can imagine. You can realize that with a semi-algebraic set. And Niev says that you can do that with an oriented matroid of rank 3. And Niev also says that you can do that with a polytope without bound on the dimension. Okay? So like the dimension, like in Niev's proof, the dimension of the polytope will depend on your semi-algebraic set. And then Richter-Gebert proved that you can do this. This 4 is due to Richter-Gebert. That 4-dimensional polytopes are enough. That every bat that you can imagine already happens in dimension 4. Okay. And as a corollary, we get what I was like advertising from the beginning, which is that it is hard to decide whether something is the phase lattice of a polytope. Because if it was easy, I would take some semi-algebraic set, for which I want to know if there is a real solution or not. So I have some equations and I need to solve them. And this is a hard problem. But if realizing polytopes was easy, what I would do is I would take my hard equations, I would turn them into a polytope, then I would ask my machine that tells me whether this polytope is realizable or not. And if the polytope is realizable, then the original system of equations had a solution. Okay, and this is not so the corollary is the realizability.
The semi-algebraic set is the solution set of some set of equations.
And you don't know if it's empty or not.
So S really is the set of equations.
I mean,
S is the set of equations.
no. So okay, I'm doing two statements. So in this statement, this is the set, and this is correct. But if you like go into the proof, what one does is take the equations defining S and turn them into an oriented matrix or a polytope.
So that's hidden.
Yeah, definitely. Yeah. So it's not a corollary of the theorem as stated. It's a corollary of the proof, and even more because, of course, like you need to know that you are not hiding the cost in transforming the equations into the polytope, right? So you can, like in polynomial time, find the polytope associated to the equation. So there is more than like it's not a corollary of the theorem, but of the proof, definitely. So realizability is hard. So this is what I mentioned, that this is existar complete. Okay, and existar is the problem of deciding whether there is a real solution to a system of polynomial equations. Okay, and in particular is this NP hard. We have that these realization spaces can be homotopy equivalent to any simplicial complex. So they can be in particular disconnected, but you can make, you know, like anything. And you have that you can have, that you need all algebraic numbers to realize oriented matrices and polytopes. Okay, in particular, like you cannot do it only with rational numbers.
It's supposed to be clear that algebraic numbers are enough somehow, whatever problem.
Yes, that's a good question. It's also hidden in this exist are complete. The realization space of a polytope, as I defined it at the beginning, it is a semi-algebraic set, okay? Because you have some polynomial equations arising from the fact that, you know, that the faces are faces and things are at the right side. So any polytope, the set of all realizations is a semi-algebraic set, and those contain algebraic points. You know, you can have non-algebraic points inside your semi-algebraic set, but there is always at least one algebraic point, like one point with algebraic coordinates inside. So every polytope admits an algebraic realization. By algebraic realization, I mean an realization with all the coordinates being algebraic numbers.
It sounds like you almost just said that the deciding realizability is the exist R problem for a semi-algebraic set.
Yes, it's equivalent. It's equivalent. But in particular,
It is explicitly.
it is explicitly. Yeah. So if you know how to solve semi-algebraic sets, you know how to realize polytopes, and if you know how to realize polytopes, then you know how to solve semi-algebraic sets. And this is this complete.
Is there a subset of this that are easier once you know parts? Suppose you know a polytope is realizable. Do you know it's easier to decide whether it's realizable over the rationals or over the algebraic numbers, or it's easier to decide whether it's connected or non-connected?
I mean, I can twist your question to answer yes or to answer no. You know, like, if it depends on how much you know. If you know everything, then it's very easy to.
No, you know only realizable. Can you deduce the rest?
No. If you only know realizable, as far as I know, I don't think it's much easier. You know, it's like if you know that the semi-algebraic set is non-empty, is it easy to know that whether it is? I mean, I don't know the details, but I don't think so. Okay. So let me give you just some hints of the proof. Okay. And what I'm talking about is not necessarily about Niev's original proof, but there's been a lot of simplifications later on. Okay. So the first one, it's very important, is due to Shor. This simplifies a lot the proof, which is at the level of semi-algebraic sets. It is enough to consider semi-algebraic sets in which the variables are ordered. And all the equations look like that. So what Shor said is that every semi-algebraic set is stably equivalent to a semi-algebraic set that looks like this. And of course, then you have to do a lot less of work because you only need to understand additions and multiplications. Okay, so like the goal is to encode a semi-algebraic set in an oriented matroid, So you are supposed to encode any polynomial equation, and Shor says, well, if you know how to encode addition and multiplication, then essentially you know how to do it. Okay? And it turns out we know how to do that since the 1850s. This was done by von Staudt, and the famous von Staudt constructions that allow you to multiply and add with points and lines. Okay, so these are the von Staudt constructions, and essentially say that in a projective scale, if you have a configuration with all these collinearities, if this is x and this is y, then this is x plus y. Okay, and if this is x and this is y, then this is x times y. And let me give you, let me see. I can make like a very quick proof for that. So what I'll do is I'll send this line to infinity. Okay, this one here. So then these two lines are parallel and these two lines are parallel. Okay, so the first picture looks like this. Okay, and I have this is q, and this is q prime. And these two lines are parallel, and these two lines are parallel, and this is x, and this is y, and this is x plus y. And you see from the parallelism that these two triangles are similar, and they are actually just one translation of the other. So if this length was x, this length is x. So, and if this is y, this is x plus y. Okay, so this is the first of the, like the one that for addition, and for multiplication, this simplifies to something like this. And so now what I've sent is this line to infinity, and I have this line to be parallel to this one, and this line is parallel to this one. And again, this 0xq is similar to 0xyq, and 1qx is similar to yqxy, and the ratio is the same. And you get that 0x divided by 0,1 equals 0xy divided by 0y, and therefore 0xy equals 0x, 0y. Okay? So, of course, there is some work to do, but this is essentially how you prove the universality theorem for oriented matrix. So you start with your semi-algebraic set. You use Shor to turn it into easy equations, and then you use von Staudt to turn these equations into collinearities and line arrangement, and you get an oriented matrix of rank 3 that every solution, like every realization, corresponds to one solution of this semi-algebraic set. So this is the universality theorem for oriented matrix. How do you go to polytopes? You use the Lorentz extension that encodes oriented matrix into phase lattices of polytopes. And this way you get the universality theorem for polytopes. Okay. And here you also see why Neuf doesn't have a fixed dimension for his polytopes, because the number of points in my point configuration that depends on the complexity of my semi-algebraic set. And if I do it planar, I'm only increasing the number of points, but not the dimension. But if I do the Lorentz extension, every time I win a dimension, every time I do it, so I cannot bound the dimension. Okay? So Richter-Geber then used a different set of tools to prove the universality theorem for four-dimensional polytopes. Okay? And now we also know that this is also true in dimension 4. I don't know if there is any question. Okay, so one thing you see here is that it is crucial to have, a lot of lines that are concurrent onto the same point. Okay, so this is a highly non-generic arrangement. And one could think that this is, let's say, that this is needed. That in exchange, if you have arrangements that are uniform means like there's no 3 points in a line, okay, so in general position in some sense, then you would not be able to have these things. But this is false, and this was already noticed by Neuf. And there are some tricks. Of course, not every semi-algebraic set you will be able to encode with something which is generic, because generic things have open realization spaces. Okay, they are stable by small perturbations, but that's the only constraint you have. Okay, so if your primary semi-algebraic set is open, then you can choose your oriented matrix to be uniform. Okay, and by uniform you have to imagine just general position, so no 3 points in a line. Okay, and you could think, what's the equivalent statement for polytopes? The equivalent statement for polytopes being generic would be polytopes being simplicial. Okay, so you don't have d plus 1 points in a hyperplane. Okay. And here's something that does not work is, okay, you take Neuf's universality theorem for uniform oriented matrix. So you find an oriented matrix which is uniform in general position that has your desired realization space. And now you want to turn this into a polytope, so you apply the Lorentz construction. Okay. What fails there is that, like when I do a Lorentz lifting, I have a lot of points in a hyperplane. Actually, all the points except for 2 lie in a common hyperplane, and for every pair of points that I lifted. So this is highly non-simplicial. Okay, do you see the problem? So even if you start with something that is extremely nice, when you do the Lorentz extension, then you lose this property. So I promised I'll give you a result of mine in every talk. So here's mine. Here it is. So this is a theorem I proved with Karima Di Prasito in 2016, and says, let me summarize it as universality for simplicial. I have another word which is neighborly polytopes. Okay. And the statement says, for every open primary basic semi-algebraic set, there is a simplicial neighborly polytope whose realization space is stably equivalent to that open semi-algebraic set. So if it is simplicial and neighborly, then it is particular simplicial. So this is missing something that was missing in this picture. But so the techniques we use are different. So we don't use Lorentz extensions. We do preserve this general position, but we also need to increase the dimension, depending on the semi-algebraic set. Our increase of dimension is proportional to the size of the original oriented matroid. So we do not have a theorem that would say a 4-dimension. This is an open question. I think Karim is working on it, so maybe it won't be open for a long time. But so this is the open question for today. Let me just, for completeness, tell you what this word neighborly means. Okay? So imagine I give you a polytope with n vertices, it's in dimension d, high enough, and I want to ask you what is the maximal number of edges that such a polytope could have. Well, like, I don't know, if worst or best case scenario, you have n choose 2, right? Every pair of vertices forms an edge. Okay? And now I can ask you how many two-dimensional faces can I have? In the worst or best case scenario, you'll have n choose 3, right? Every 3 points will form a face. So we'll say a polytope is k neighborly if every subset of k vertices forms a face of the polytope. Okay, the first question is whether these exist. I mean, the trivial answer is yes, because the simplex has this property for every k. The next answer is, except for the simplex, you cannot go beyond k equals to d halves. The best you can do is k equals to d halves, and this you can do, okay? The one polytope that achieves this is the cyclic polytope. I don't know if you have heard about it. If you take the moment curve that takes t to t squared t to the d, and you take n points on this curve, and you take the convex hull, you get a polytope that is neighborly. So when I say neighborly without saying which is the k, it means d half, which is the best possible. So you get a polytope that is d halves neighborly, and whose combinatorial type does not depend on which points you chose. Okay, that's why we talk about the cyclic polytope. Actually, when they were first discovered, the claim was that this was the only polytope that had this property of being neighborly. But this is false, even very false. Okay, so if you remember yesterday about the number of polytopes that there are, until recently, the best lower bound for the number of polytopes was from a family of neighborly polytopes. Okay, so you have as much variety of neighborly polytopes as we know to have variety for normal polytopes. So they are actually, say, very common, or at least there are a lot of different ways of getting a neighborly polytope. It is maybe not so surprising that, if you want to have a lot of combinatorial types, you need to have a lot of ways of distributing the vertices among the facets. So you want to have a lot of facets, and neighborly polytopes have a lot of facets, and that's why you have a lot of variety. Maybe I forgot to say you the most important things about neighborly polytopes and cyclic polytopes is that, so they maximize the number of faces in all dimensions until d halves, just because they define it that way, but they also maximize the number of faces for the whole dimensions. Okay, they all have the same face numbers in every dimension, and this number is maximal among all d polytopes with n vertices. If you have a simplicial neighborly d polytope with n vertices, then it will have at least as many faces as any other polytope in dimension d with n vertices. This is the upper bound theorem by McMullen. And I guess it's a good time to end.